So here is one way we could derive such a second order curve, such a parabola, and then how to interpret that to improve our reliability estimate. So the SORM algorithm, just for completeness, let us put here, we find u star, the minimum distance point, and the distance beta. We are going to use these. We are going to use u star, and we are going to use this distance beta to develop the second order approach. We will also need the direction cosines that the minimum distance point makes with the origin. So the first step is to rotate our independent standard normal axis system. So let us say we rotate the u-axis system to the u tilde axis system, and the purpose of doing that is to have a simpler description of the second order parabola or paraboloid that we want to fit at the minimum distance point obtained from SORM. So we stick to the minimum distance point. That is the answer given by SORM. So let's say we take one of the axes, the last one, u tilde n, to coincide with that minimum distance direction, which is given by the direction cosines alpha, which we just stated on the left part of your screen. So that is the formal description of the transformation. The u tilde is r times u. R is the transformation matrix. So if we do it this way, then our paraboloid can be given in terms of the nth axis, the last one in the new system, in the new tilde system, is as beta, the minimum distance, plus a second order fit at the minimum distance point u star in the new coordinate system u tilde. So we need the matrix of second derivatives A. And so how do we get that? Let us do that. So A is an n by n, n minus 1 by n minus 1 order matrix defined at the point u star, and if we know what the second derivative n by n second derivative matrix is of the limit state function h at u star in the original u space, then we can derive A in terms of D using the transformation matrix. So D is the n by n second derivative matrix of H evaluated at u star, and using the transformation R that we already have, we get A in terms of the D. And because A is n minus 1 by n minus 1, we discard the last row and the last column obtained this way. So to summarize, we find the minimum distance point in the independent standard normal space just as we did in form. So that would be u star. We find the beta of the minimum distance. We find the direction cosines that this minimum distance makes with the origin. And then we try to fit a paraboloid at that minimum distance point. So we are basically going towards finding the curvature of this paraboloid. So we transform u to u tilde, and we know how to get that n by n minus 1 square matrix A, because we can compute D, and then from there we can get A. So these are the mathematical steps, and then it can be shown, and I have the references at the end of this slide, is the improved failure probability would be the SORM failure probability phi of minus beta times a correction factor. This correction factor takes into account the curvature of the limit state. So sometimes it could be more than 1, sometimes it could be less than 1, depending on whether your failure region is concave or convex, depending on whether you're undercounting or overcounting failure probability. Obviously, it cannot give the exact answer, but it does make an improvement, as we will see by solving the same problems we did before and resolving them with SORM. So we can express this if we just take the first term in that expansion. We end up with the principal curvatures of that paraboloid which we fit in the U tilde system if we know the eigenvalues of the matrix A. And the curvature is positive for convex failure region because we need to reduce the failure probability, so the denominator has to be more than 1 if PF2 has to be less than phi of minus beta, and kappa has to be negative if we have a concave failure region, in which case we need to increase the failure probability obtained by FORM. So that's an intuitive explanation of what is going on. As I said, for further reading, I refer you to these very important 2 papers, the one by Broughton coming out in 1984 and the other by Professor Deriving et al. Coming out in 1987.